So last time we looked at just the basics about magnetism and sort of the idea behind domains and that type of stuff. And unfortunately, we're not in my lab. Otherwise, I could show you just so many cool toys and gadgets that use them. Magnets are one of the handiest things around there. You use them for so many things. For connecting toy trains when you're a kid, to opening and closing clasps on like a purse or stuff like that. Like magnets are used for so many different things because they're so portable. They can be so strong. Then all your headphones, your microphones, they're used for so many different things. They're a lot more portable and handy than electric field, and there's so many cool things that you can do with them. And just go onto YouTube and look up cool magnetic toys or cool magnetic gadgets, and you can spend hours just watching the videos that are out there, especially things like ferrofluid and stuff like that. Just super, super cool stuff. Okay, so make sure you spend some time doing that when you're supposed to, I don't know, be doing like your ELA or your Mr. Bayek's history. Go do that instead or something like that. It's lots of fun. Anyway, so today we're going to look at a little different aspect of magnetism. Magnets aren't the only place that you can actually find magnetic fields. And there's a guy way back when named Oersted. Sounds like a made-up name, but it's not. And he found something sort of by accidental and good discovery, really important discovery, pretty much by accident. He found out that magnetic fields actually can come from electrical wires with current in them. If you remember, the symbol for current is a capital I, electrical current. And he found this sort of that he's a big guy for electromagnetism and that type of stuff. And basically, often they find stuff by accident, but they're working with electricity and all that kind of stuff, and all of a sudden a compass that happens to be nearby all of a sudden starts moving, and it's like, holy smokes, this wire with current going through it has a magnetic field coming from it. So that's really strange. So they tried to find out what shape the magnetic field was around the wire. Is there a north end? Is there a south end? Like sort of how this worked. And it was actually really, really tricky and hard to find. And I'll sort of show you why. There's a great video here that's going to show it really, really, really well. This person has a wire through like a piece of plexiglass, something like that, and he's going to put current through it. I'll sort of skip through little things here. What he does is he sprinkles iron filings on the piece of plexiglass or clear glass or whatever that happens to be, and then he puts a current through the wire. And if you can see, and then he sort of like taps a little bit, and you can see the iron filings sort of taking a shape around the wire. And I'm going to pause it right there. It's kind of really strange because it's going around the wire. And that was one of the trickiest things about this, is when Oersted was working with this, the actual magnetic field actually went around the wire. It didn't actually go into the wire or out of the wire. It actually went around the wire, which is really, really, really strange. So there's no real south end. There's no north end to the wire. You just have this magnetic field going around the wire in a circular shape. So it was kind of weird. It's not even a spiraling out from the wire. It's concentric circles around the wire. So this is one of the reasons it actually took them a while to sort of figure out what the magnetic field actually looked like coming from a wire. So if we sort of do some sketching here, here's my wire, something like this, and there's current going through it. The magnetic field actually goes around the wire in circles. Not just one set of circles. There's like infinitely many circles, and there's bigger ones and there's smaller ones, and it's really, really, really kind of strange how this works. And it was a pretty big puzzle, but it actually goes around the wire. And you'll often see pictures and diagrams in what this actually looks like, and we'll get to that in just a second. But it's kind of weird. We got concentric circles of magnetic field going around the wire, and it only exists when the current is actually running. So you turn the current off, the magnetic field disappears. Now the thing is, if you put a compass around here, the compass will actually show a direction. The magnetic field is actually going around in a direction. It's not random. Okay? Now, for example, suppose the current was coming this way. There's my electrical current. I can tell you that the magnetic field would be coming up this side, wrapping around the other side, and then coming this way. So on the side that's closest to us, it's going up this side, and then tucking in behind, and then coming from underneath, and then back towards front of us. So we'll get into a nice little diagram of sort of how this works. But it's this is where a little trick kicks in, a little thing that they've been using for, well, for a super long time. We use a little trick called the right-hand rule. So you might hear something called the right-hand rule, and sometimes we call this right-hand rule number 1 because there's more than one, to sort of show you which way the magnetic field's actually going. So to use the right-hand rule is actually really simple. You make a fist and stick your thumb out, and your thumb shows the direction of the current. So in my picture, my thumb is pointing towards the left, and then my fingers show which way the magnetic field is wrapping around the actual wire itself. Okay, so if we go back to our PowerPoint from before, you'll see something like this, and this is a little picture of it. So here we have how the right-hand rule works. Your thumb is the direction of the current, and then your curved fingers show the direction of the magnetic field going around the wire. Okay, so that's generally how the right-hand rule actually is drawn, actually works. Now, it can be a little bit tricky sometimes when you draw things like this, because drawing loops and circles, that can get a little messy. So another really common way to do it is to look at critical points above and below. So remember that vectors are arrows. Okay, so vectors are arrows. You know, they go towards you, they go away from you, they go left, they're arrows. So if I went to the very, very top here, if I was looking at this wire, the very, very top, the magnetic field at the top is going away from me. So that's going away from me. It then goes down behind the wire, and then comes down here, and down here it's going towards me, and then it loops back up this side. Well, this is the two critical points we can look at, the top and the bottom. So if an arrow is coming towards you, you see the tip of the arrow. So that's what we often draw, is just the tip of the arrow. And if an arrow is going away from you, you see the feathers on the back of the arrow, which would be the top. So it's common to draw a little X, which represents the feather of an arrow. So instead of drawing loops, which can get kind of confusing, it's really common to draw X's and dots. And they always pair up because they represent two parts of a circle. So on the top of the same wire, draw my current here, it's the exact same wire we have above. Above the wire, the magnetic field is going away from me, just like it is up here. And down here, the magnetic field is going towards me, just like it is down here. And then we don't really worry about the front and the back and that type of stuff. We just draw something like this. Okay, and that's a nice little way to draw vectors. And it's not just for magnetic fields. You can use for electric fields, force. It doesn't make any difference. For example, if we drew a door, so here's a door, and there's the door handle, and you open the door, and you were going to push the door, this X would represent the force vector because you are pushing the door away from you. Okay, but if you would pull the door, then it would be the arrow ahead because it's coming towards you. This, if you pull it, then the force is actually going towards you. So any vector that goes away from you, you can use an X. Any vector going towards you, you can use the tip of the arrow or a dot. Okay, so that's basically how it works. Okay, but this is the right-hand rule for figuring out the direction of the magnetic field around wires. Okay, so let's look at a different setup, a little different diagram here. So let's look at this one right here. So we have a wire that's sort of bent in sort of like a weird wiggle shape. The current is going down towards left. So if I want to do my right-hand rule to figure what the magnetic field would look like, well, I'm going to take my thumb, I'm going to point my thumb towards the right, and then if I do that, if I loop my fingers around and sort of like do like a bending finger motion, if I look at the top of the circle type path, my fingers are actually coming towards me. I'm looking at the tips of my fingers when it's here, and then underneath they are actually going away from me. And that same general trend would then follow all the way along the wire. And you should always draw them in matching pairs. They sort of match up to each other across the wire. So that is the direction of the magnetic field above the wire and below the wire. So above the wire, the magnetic field would be coming towards me, and below the wire, the magnetic field would be going away from me. Okay, if I would draw this the other way with like a loop type picture, it would be going towards me, it would come down the front, and then go back down behind, and then up behind the wire, something like that. Okay, so that's how we can draw the X's and the dots for something like this. So now let's try this one. Here we got like a U-shaped wire with a magnetic field around it. I want to figure out which way the current is going. So what I'm going to do is I'm just going to use the right-hand part over here. And if I do that, I'm going to stick my hand up. I'm going to make my right-hand rule. So I got like my fist with my thumb sticking out. My current is either going up or down. So I'm going to try having my thumb point down on the right-hand side. If I have my thumb pointing down on the right-hand side, on the left side of the wire, my fingers are going away from me, and on the right-hand side, they're going towards me. Well, that seems to work. Let me try flipping it on the right-hand side. If I look at the right-hand side of the U and have my thumb pointing up, on the left-hand side of the wire, my fingers are coming towards me, but I've got X's, not dots. So it sounds like my first try was right. If I have my current going down this way, I have my thumb pointing down, and on the left-hand side of the wire, my fingers to be pointing away from me, and on the right-hand side of the wire, my fingers tips come back towards me. So it looks like the current will be coming down here, wrapping around, and then coming out that side over there. So you could have used the left side of the U or the right side of the U. It doesn't make any difference. But again, just using the basic right-hand rule to figure out which way the current is actually going.